This course is about designing a residential irrigation system. We'll begin by measuring the job site and preparing a plot plan and determining the available water supply. From there, we will discuss proper sprinkler selection and layout, dividing the system into zones, sizing and laying out pipe, and finally, completing the design to create a finalized plan. The design process begins with a visit to the job site. In order to make the most of your visit, you'll need a 250-foot tape measure, information about water pressure in the city water main at that location, a pressure gauge, and a clipboard with graph paper and a pencil to help you record your observations quickly and efficiently. It's important to measure the property carefully because inaccurate measurements can lead to problems with pressure and coverage that could require expensive repairs after the installation. We'll start by getting accurate measurements of distances on a property. The easiest way to do this is to lay down your 250-foot measuring tape along the curb of the property. Use this measurement to choose a scale on your graph paper and draw the edge of the property at the bottom. Walking behind the tape measure and looking straight back into the property, you can line up the edges of structures and landscape elements with the marks on the tape measure. On the graph paper, mark the location of the edges of all major elements of architectural and landscape design, including the location of the house, driveway, sidewalks, pools, decks, or patios, and significant landscape elements like trees, shrubs, landscape beds, and any borders between different kinds of plantings. Once you have measured the property from the curb, repeat the process with the measuring tape stretched along the side of the property at a right angle to the curb. You'll now have two coordinates for everything on the property, and you will be able to easily draw the property to scale on your graph paper as you go. For houses with complex back or side yards, you might need to repeat the process along the back edge of the property and on the other side, but 2 passes are sufficient for most properties. In addition to properly measuring the property, there are several other important pieces of information to note that will affect your design. Identify the orientation of the house with an arrow pointing north and note which parts of the property are full sun, part shade, or full shade. Also note any plant material covered by overhangs that will not receive rainfall. Having drawn in the borders between plantings, note what is planted where, especially for plants with significantly different water requirements. Indicate the direction and grade of any slopes on the property, and the direction and speed of the prevailing wind. Additionally, know your local codes and identify the place where you will tap into the water supply, and find a location near an outlet for the controller. Finally, confirm the soil type before leaving the property. You can perform a squeeze test to determine whether the soil is predominantly clay, loam, sand, or some mixture of the three. When a moist ball of soil is squeezed, clay soil will retain its shape when poked, loamy soil will break apart when poked, and sandy soil will completely fall apart before forming into a ball. A plan drawn to scale with complete and proper site information is essential for completing a design that will enable easy installation of an efficient, easy-to-maintain irrigation system. The primary limitation on the design of an irrigation system is the maximum allowable flow rate. This determines how many sprinklers can operate at a single time, and will affect how the sprinklers are grouped into zones and how long those zones need to run. There are 3 tests used to determine the maximum flow rate available for an irrigation system. Number 1. The maximum flow rate with a pressure loss at the meter less than 10% of the city's main static pressure. Number 2. 75% of the meter's maximum allowable flow rate. And number 3. The maximum flow rate with a velocity under 7 feet per second in the service line for copper or steel service lines. The maximum allowable flow rate will be the lowest of these 3 numbers. Let's run through a calculation for a sample system. For this calculation, you'll need 3 pieces of information. Number 1, the minimum static water pressure of the city main. This information can be obtained from the water purveyor. You can verify on-site at a spigot with a pressure gauge threaded onto a hose adapter. Number 2, you'll need the water meter size, which is usually stamped onto the top of the meter. And number 3, the size of the service line. Let's consider an example where the static water pressure is 75 psi with a 3/4 inch water meter and a 3/4 inch service line. What's our maximum allowable flow rate? First test, the maximum flow rate with a pressure loss less than 10% of the city main static pressure. Since our static water pressure is 75 psi, the maximum pressure loss is 7.5 psi. Consulting the pressure loss through water meters chart, we see that the maximum flow rate under the 7.5 psi pressure loss is 20 GPM, with a pressure loss of 6.5 psi. Second test, 75% of the meter's maximum flow rate. Returning to our chart, we see that for a 3/4 inch meter, the highest pressure loss recorded is 15 psi at 30 gallons per minute. This means that 30 gallons per minute is the maximum flow rate for this meter. 75% of 30 gallons per minute is 22.5 gallons per minute. And the third test, the maximum flow rate with a velocity under 7 feet per second in the service line, for steel and copper service lines. We've got a 3/4 inch copper service line, so let's have a look at the chart for type K copper tube. We can see that for 3/4 inch pipe, 9 gallons per minute is the maximum flow rate, with a velocity under 7 feet per second, clocking in at 6.61 feet per second. The lowest flow rate that passes all 3 tests is 9 gallons per minute, so we'll use this one to design the system. With all of the site information in hand, you are ready to divide up the plan into separate watering zones called hydrozones, based on the watering needs of the plant material. There are 3 variables to consider: sunlight and weather exposure, area size and shape, and the type of plant material. First, divide areas that have significantly different sunlight and weather exposure. If a treeless front lawn is on the south side of a house, it will require significantly more water than a shady backyard on the north side. To allow the system to adjust for the different water needs, these areas need to be in separate hydrozones. Similarly, if a landscape bed is wholly covered by an awning or an overhang, it should be separated into a distinct hydrozone from landscape beds that receive regular rain. Next, divide up areas according to their size and shape. A large turf area will require different kinds of sprinklers than, for instance, a narrow strip of turf between a sidewalk and the street. Divide these into distinct hydrozones. Finally, divide up areas with different kinds of plant material. High water usage plants like turf should be on different hydrozones than low water usage plants like ground cover or more sparsely planted shrubs. A point source strip system can provide different quantities of water to plants on a single zone, but most irrigation methods distribute water evenly over an entire watering area. Areas with different water requirements should be in separate hydrozones. This prevents a scenario where some plants are underwatered while others are overwatered. Let's take a look at an example. Suppose this is the plot plan of the property we are designing a sprinkler system for. We'll want to start by dividing the front of the house, which has full sun, from the back and side, which is part to full shade. Additionally, the side yards and the front strip are quite narrow, so we'll break them off into separate sections as well. The landscape plantings constitute another area, and in this plan, there aren't any plantings covered by overhangs. Once the plan is divided into hydrozones, we're ready to select sprinkler heads. There are 5 main types: rotors, fixed sprays, spray heads with rotary nozzles, specialty pattern sprays and bubblers, and micro or drip irrigation. Each of these sprinkler heads have advantages and disadvantages, and to understand the differences between them, let's quickly define a few terms. Radius. The radius of a sprinkler head tells you how far it sprays water. The longer the radius, the bigger the circle the sprinkler head covers. Flow rate. The flow rate is measured in gallons per minute, which is critical for determining how many sprinkler heads can run on a single zone. Precipitation rate. The precipitation rate is measured in inches per hour, and it tells you how many inches of water the sprinkler head will put onto the ground in an hour. You'll use this information to calculate run times for the controller. All of the sprinklers on a particular zone must have the same precipitation rate to water evenly. On a typical performance chart, the precipitation rate is given both for square spacing and triangle spacing. This refers to the way that the sprinklers are laid out. Square spacing refers to a grid of squares, with sprinkler heads at each corner. Triangular spacing refers to a grid of equilateral triangles, with sprinkler heads at each corner. Triangular spacing is more efficient and has higher precipitation rates. Operating range. Each sprinkler type works best within a limited range of operating pressures. While the pressure of an irrigation system is in many ways determined by the location, you can add pressure to a system with a booster pump and regulate pressure with pressure regulating valves and sprinkler heads. Once the design is complete, we will calculate the operating pressure at the last head to ensure that it is operating within the recommended range. Now let's take a quick look at each type of sprinkler. Rotors come in different sizes with different radius ranges. Mini rotors generally have an 18 to 36 foot radius range. Standard residential rotors typically have a 22 to 50 foot radius range, and sports field rotors generally throw water between 45 and 75 feet. Now that's what I call a home run. Sorry. The radius range is affected both by the water pressure at the sprinkler head and the size of the nozzle used. Rotor flow rates and precipitation rates vary quite significantly depending on which nozzle you use. A standard residential rotor will have different nozzles with flow rates ranging from 0.5 to 6 gallons per minute and precipitation rates from 0.15 inches per hour to about 0.8 inches per hour. Determining precipitation rates for rotors involves an extra step in the calculation. The precipitation rates listed here on the chart are based on a half-circle rotor. However, if your plan calls for a full circle spray pattern, the rotor will only go over the full circle area once in the same amount of time that a rotor spraying in a half-circle spray pattern would water its spray area twice. Now this means that to calculate the precipitation rate for the rotor adjusted to a full circle arc, you will need to divide the precipitation rate on the chart by 2. Similarly, if a rotor is adjusted to a quarter circle pattern, you will need to multiply the precipitation rate by 2. Now this has consequences for your choice of nozzle and how you zone the rotors. If there is a mixture of spray patterns on a rotor zone, you will need to choose nozzles that ensure that the precipitation rate for each rotor is the same. For instance, if you use a number 3.0 nozzle on a quarter circle rotor, you'll need a number 6.0 nozzle for a half circle rotor on the same zone in order to match the precipitation rates of the rotors. In general, rotor precipitation rates are lower than those of fixed sprays, so it is not a good idea to mix rotors and sprays on a single zone. Rotors operate best between 30 and 60 psi. Commercial rotors will perform at pressures up to 70 psi, and athletic rotors require pressures between 40 and 80 psi to operate. The term fixed spray refers to all spray heads with nozzles that emit a fixed fan of water over the watering area. Depending on the nozzle used, a fixed spray will have a radius from 6 to 18 feet. Flow rates depend on the radius and the arc spread, ranging from 1.5 to 6 gallons per minute. Fixed sprays automatically match precipitation rates based on how large the arc is, and have much greater precipitation rates than rotors, ranging from just over 1 to just over 2 inches per hour. Fixed sprays operate best between 20 and 50 psi. Rotary nozzles are installed in spray heads and have the low precipitation rates of rotors, but work in smaller areas like fixed sprays. A rotary nozzle radius ranges from 13 to 30 feet, uses between 0.2 and 4 gallons per minute, and has precipitation rates around half an inch per hour. Rotary nozzles operate extremely consistently between 30 and 50 psi. There are a number of specialty nozzles, bubblers, and other add-ons to an irrigation system designed to solve particular problems. Fixed sprays and rotary nozzles both have side strip and end strip nozzles that water thin rectangular areas about 5 feet wide and 15 feet long. This is a great solution for the strip of grass between a sidewalk and the road. Bubblers can be used to supply supplemental water to trees or other individual plants with particular water needs. Operating ranges vary based on the nozzle. And finally, micro or drip irrigation can be used to provide water to landscape beds, ground cover, or sparsely planted areas. This irrigation method relies on the use of many small emitters with a very small radius, including drip emitters, drip bubblers, or microsprays. There are two main types: inline drip irrigation, where the emitters are built into the tubing, and point source drip irrigation, where individual emitters are punched into the tubing by the plant. With inline drip irrigation, flow rates can be calculated per foot of tubing, and precipitation rates are very low, from 0.15 to about 1.5 inches per hour. With point source irrigation, flow rates are calculated per emitter and precipitation is measured in gallons per day per plant instead of inches per hour. The operating range for most micro or drip irrigation is 15 to 25 psi. Alright, let's get back to our design here. Because of the large areas of turf in the front and the back, rotors are a natural choice for these areas. The strip in the front is quite narrow and is surrounded by concrete and the street on either side. Spray nozzles will work best in this area. The side yards are also narrow, but it's best to use rotary nozzles here, and we'll go ahead and install inline drip irrigation in the landscape bed. That's a good general game plan, but now it's time to specify the details. Which sprinkler? With which nozzle? And what flow and precipitation rate? To begin, let's consider the last piece of information we talked about gathering at your site visit: the soil type. Soil type matters a lot when you're installing drip irrigation because water travels very differently in different soil types. In clay soil, water spreads out and infiltrates the soil slowly, 0.1 to 0.4 inches per hour. In loamy soil, water spreads out and down more evenly and infiltrates the soil more quickly, about 0.3 to 0.9 inches per hour. And in sandy soil, water quickly drains downward, infiltrating the soil at 0.7 to 1.25 inches per hour. It is best to choose sprinklers with precipitation rates that do not exceed the soil infiltration rate. Another important consideration is the grade of the property. When watering on slopes, you need to be attentive to the effects of gravity and potential problems with runoff. So it is important to use lower precipitation rates and either increase spacing as you move down the hill or eliminate sprinkler heads at the bottom altogether. The key idea in sprinkler layout is head-to-head spacing. Now, what do I mean by that? When laying out the sprinklers, the radius of one sprinkler should reach the head of the sprinkler next to it. The maximum allowable distance between sprinklers is 120% of the sprinkler radius. There are two basic styles of head-to-head spacing: triangular spacing, which is the most efficient spacing method, and square spacing. In the case of triangular spacing, the sprinklers are laid out at corners of equilateral triangles in a triangular grid, with each side of the triangle less than or equal to 120% of the sprinkler radius. In the case of square spacing, the sprinklers are laid out at the corners of squares in a grid. Square spacing is less efficient than triangular spacing. There is a weak spot in the middle of the square, so each side of the square should be less than or equal to 110% of the sprinkler radius. Sprinkler spacing should be reduced in sites with the prevailing wind over 4 miles per hour. For triangular spacing, a prevailing wind of 4 to 7 miles per hour dictates a maximum spacing of 110% of the radius, and a prevailing wind of 8 to 12 miles per hour requires a maximum spacing of 100% of the radius. For square spacing, spacing should not exceed 100% of the radius in areas with winds from 4 to 7 miles per hour, or 90% of the radius for areas with winds of 8 to 12 miles per hour. When laying out the sprinkler heads on the plan, be sure to indicate the sprinkler type, nozzle size, and flow rate for each sprinkler head. The limiting factor on the size of zone is the number of gallons per minute the sprinkler heads on that zone consume. You should design zones to use no more than 80% of the system capacity as determined above. So, for our example, that's 80% of 9 gallons per minute, or 7.2 gallons per minute. Consulting specifications for a 1-inch valve, we can see that this is well within its operating range. Start creating zones by grouping the sprinkler heads in each watering area together. If the total number of gallons per minute in the watering area is greater than 7.2, divide that area into multiple zones. Connect sprinklers with lines to indicate the pipe layout, and draw in a valve indicating the zone number, valve size, and flow rate. Each zone must connect to a main line that runs from the point of connection to the final valve. Where possible, group valves together into manifolds for ease of installation and maintenance. It's much easier to locate and service a group of 3 valves than to find each one individually in the yard. The next step is to determine pipe size. The phenomenon that governs pipe sizing is friction loss. This is a loss of water pressure due to the friction created as water moves through the pipe. Pipe sizing affects friction loss in this way. When relatively little water is moving through a large pipe, the water moves very slowly with minimal friction that has very little effect on the pressure at the end of the pipe. On the contrary, when a large amount of water moves through a relatively small pipe, the water moves quickly, and this generates a lot of friction, which reduces the pressure at the end of the pipe. To properly size the pipe, you'll need a pipe chart and 2 simple rules. Keep the velocity below 5 feet per second, and count flow rate from the end of the line backwards. You'll notice on the pipe chart that some values are darker than others. The line between them is at 5 feet per second. This is the point where the velocity causes friction loss too high for efficient system design. This means if you're using 1-inch class 200 pipe, you'll have 5 rotors with a number 3.0 nozzles at 50 psi using 2.7 gallons per minute each. That's 13.5 gallons per minute and within the acceptable flow range of the pipe. But 6 sprinkler heads would be too many. That would be a total of 16.2 gallons per minute, which would create a velocity of over 5 feet per second. In this case, use 1 1/4 inch pipe for the first sprinkler head. It's at the first sprinkler head that 16.2 gallons per minute are flowing through the pipe. After that head takes its 2.7 gallons per minute, the next 5 heads are only using 13.5 gallons per minute, and you're free to step down to 1-inch pipe at that point. When feeding pipe to a zone, it is best to feed the line from the valve to the center of the zone so that there is less friction loss than there would be at the last sprinkler of a long end fed run. T and H pattern layouts are common in sprinkler design for precisely this reason. When sizing pipe, always begin with the last head. Determine the minimum pipe size necessary to maintain a velocity below 5 feet per second at the flow rate of that sprinkler. Then move to the next sprinkler head. Add the 2 flow rates together to get a new flow rate, and find the right pipe size for the new flow rate. Evaluate the pipe size at each new sprinkler head. Once the pipes are laid out and sized, make sure that the system will operate properly by calculating the friction loss to the furthest sprinkler head. Start at the last head in the largest zone and multiply the friction loss value by the table by the length of the pipe. Then divide by 100. Alright, hang in there, we're almost done. There are just a few more details to consider before the plan is complete and ready for installation. You'll need to identify the point of connection, valve locations, and the location for the controller and any sensors on the system. Local codes determine where you are allowed to connect to the water line on the property. Other considerations about the point of connection include where the meter is located and the easiest access point for tapping into the water line. Identify the point of connection on your plan and then route this pipe to the location of the backflow preventer. The backflow preventer should be placed in an easy to access place for testing and maintenance purposes. But that is still out of view, like behind a tree or a shrub. It's pretty common. The main line then continues around the property to reach all valve locations. Finally, indicate on your plan the location of the controller and any sensors on the system. When locating the controller, you'll need to place it near a power source, but also in a location that is not landlocked by concrete, so that you would not be able to feed the control wires directly into the ground. When locating rain or solar sensors, be sure that there are no tree branches or other obstructions that will prevent them from working. And make sure that they are high enough to be affected by the sprinklers themselves. If there are any soil moisture sensors, identify a representative location for each sensor. And we're done. Congratulations! This completes the design of a basic residential irrigation system. Your plan is now complete and you are ready to install. Go get your hands dirty.